Thank you, Lillian, for joining us. I'll hand it over to you.
Awesome. Just a quick check that everyone can see the screen, my PowerPoint. Perfect. All right. So my name is Lillian Williams, as I was introduced by Fanny, and I graduated maybe 3 weeks ago from Auburn for the second time and was very excited to come back and get to keep talking about my research. So I had an evaluation of construction stormwater detention measures using our full-scale techniques under regional conditions. So this project was partnered with the Nebraska Department of Transportation and through Auburn University, specifically the Stormwater Research Group. So thank you to Nebraska. So quick presentation overview. We're going to have a little bit of background in literature, so why we do things and then where we pulled information from, credible sources, hopefully, and then a little bit of the research plan methodology and construction to get us set up for testing, and then go into what happened during silt trap testing, structural clean water testing, and sediment trap testing. And then within each of those sets of tests, we identified what is called an MFEI, or most feasible and effective installation. And I'll go over that again and then just wrap up with some conclusions. So first, the background. So construction activities, as we have probably seen firsthand, have the potential to cause sediment discharge into the surrounding areas. And this can be runoff rates of 10 to 20 times greater than those of ag lands, and then 1,000 to 2,000 times greater than those of forest lands, according to the EPA. So during just a short period of time, construction sites can contribute more sediment to streams than can be deposited naturally during several decades. This resulting siltation and other pollutants in the sediment can cause chemical, physical, and biological harm to our nation's waterways. For example, excess sediment can quickly fill rivers and lakes that require dredging extra and destroying aquatic habitats. So there's a lot of potential harm that could happen due to sediment runoff. So what are some ways that we try to mitigate this? First is through the Construction Stormwater General Permit. So this permit is specific to Nebraska. You might have also heard of the CGP. So that's the same type of permit. This one is just specific to Nebraska since that's who funded our research. And that's the region that we focused on. So they have a Department of Environment and Energy that issues these permits before any land disturbance. So you can think of this permit as your legal ticket to discharge stormwater. Without it, you're breaking the law and you can be fined or shut down. So how do we get these permits? You typically have to fill out a SWIP, or a Stormwater Pollution Prevention Plan. So SWIP often has a lot of detention measures implemented on the construction site itself. So these detention measures function by capturing sediment through impounding runoff, and that facilitates the settling of the particles that are suspended in that runoff. So the major principles of detention, so the governing principles or principle is really sedimentation. So sedimentation, Stokes' law, that kind of is dependent on size and density of your particles. Residence time is also a huge factor. So that allows the adequate storage volume to be provided for the storms that are sized for your region, and then it allows dewatering. So you need to be able to restore that volume for future storms, and then flow velocity. So you need to impound or otherwise dissipate the flow energy coming in. And sedimentation, based off of all of these sub-principles, function by allowing soil particles and integrated pollutants to gravitationally settle out of the water column. So the detention practices that Nebraska employs are the silt trap, sediment trap, and sediment basin. So these practices are selected based off of the contributing drainage area of your construction site, right-of-way availability, design life, so how long you want it to last, downstream sensitivity, and upstream disturbance duration. So those are some of the factors. And then when we take a further look at each practice and compare the nitty-gritty differences, you can really see in that contributory drainage area column that the silt trap is the smallest, so it's up to 1 acre. The sediment trap is 1 acre to 5 acres, and the sediment basin is everything over 5 acres. And then with each of those practices, you see the sizes differ, and then the required dewatering device or lack of is also different. So in this project, we were asked to focus on the silt trap and the sediment trap and really optimizing those practices. And this is the silt trap plan view. So you can see it has that 6 foot wide and then it's 1 foot deep. So you have a 2-to-1 slope on this little excavated sump basically. And that is going to give you 10 feet across the top, which is typically the width of your channel. And that was the width of the channel we constructed. And then in this view, you see that there is a practice paired with the silt trap that's 2 feet downstream. So we see the flow going from left to right. And like I said, there is a practice here. It's the wattle, but it can be other practices as seen in these profile views. You have this high flow silt fence at the top, and then on the bottom you see the wattle again in another application. So this is kind of what the silt trap is looking like, just that shallow excavated sump. And then we go into the sediment trap, so that's the second biggest of the 3 detention practices. And there are 2 typical applications. So you see the roadside ditch and then the swale, the outlet swale. We decided to go with the typical roadside ditch application, which has a kind of unique feature. You go down the channel parallel to the road being worked on, and then it turns 90 degrees into your basin. And so the one on the left is what we went with. And here's a few more details. You can see the side slopes are specified. The width will be specified on the next sheet that I will show you. And then it has a type A rock riprap, and that's for the emergency spillway outlet device. And here's just some more details of that trap. There's 2 tables that specify the basin length and width based off of your drainage area, and then it also specifies your weir length based off of the same drainage area. So these are the plans that we used when constructing these detention practices. So before we went too much further into getting our hands on these practices and running the test, we had to kind of take a step back and look around what others were doing to see if we can find what we're able to implement. So we looked at states either in the area, so the Nebraska DOT, sorry, what am I saying? Other DOTs related to Nebraska were Iowa and Minnesota, and those states have kind of reputable stormwater measures or programs. They're kind of pursuing that development. So we decided to take a look at those states, and those are kind of in the Midwest region. So would have similar conditions that Nebraska would experience. And then we took a look further south just because it experiences very high rainfall. And with that high rainfall, you have to have pretty sturdy detention practices put in place. And many of the Alabama practices we've tested at our research facility. So we're pulling from all these different areas and all these different research tests that have been actually implemented in the field. And we found that there are similar core philosophies from these various state detention practices, and that's really to slow the water down, to increase that detention time, so the time that the water is able to create that sedimentation and then manage the discharge. So you can adapt these based off of the local conditions. Like I mentioned, the rainfall intensity, and then of course your drainage size kind of indicates what you need to size your detention practice to, and then the erosion risk. So the basin geometry really matters. Other things that we found from looking at different state DOT manuals was that maintenance is essential. So sediment removal and drainage upkeep are required in many of these states and on their inspection list. And then they control discharge through either weirs or risers or skimmers to improve that water quality. You see skimmers implemented in a lot of these states. And then there are other additives that enhance sediment removal like baffles and forebays and more along those lines. So I'll go into it a little bit more in our literature review. If you want the full thing, I have a very, very long thesis that you could read, but you don't have to. So let's get into our research plan. So after looking at some of this, what did we actually do with it? Like, what was the problem to begin with? So problem statement. The DOT asked us to look at their detention measures because they hadn't been scientifically evaluated. They had just been put in field use. So because of that lack of evaluation, there were opportunities to enhance those performances and develop that design guidance for Nebraska. So our objectives were to develop a methodology to evaluate these practices and compare their performance of selected practices typical to Nebraska highway construction projects in the removal of sediment. So sediment that is from construction generated runoff. And then we were to conduct replicable full-scale testing that would mimic Nebraska conditions through corresponding soil losses and runoff volumes on the silt trap and the sediment trap, and then any other identified modified installations. And then from all of this testing, we were going to identify what that MFEI, or most feasible and effective installation, as discovered from the data collection and field observations, to provide implementable design guidance for use on NDOT projects. So our 5 tasks that were developed from the objectives were that literature review that I'd kind of touched on. So this is kind of comprehensive and just really discovering what the state of the practice is, and I help in identifying potential modifications. Then we move into the design of the experimental measures and the testing methodology, and that is based off of like local Nebraska values for testing those sediment introduction and flow rate introduction. So these construction measures that we then built were to mimic the Nebraska highway conditions, what you would find on a project. And then we went into full-scale testing at the Auburn University Stormwater Research Facility. Our data analysis followed, which consisted of looking at the water quality and the sediment capture of each installation. And that culminated into the interpretation of our results to find that MFEI. So our methodology was developed in 5 stages. Stage 1 was a statewide analysis of the climate. So here I have a map of the rainfall depth and then the average, the weighted average curve number. So that kind of lets you know what's happening across the state as far as soils being lost due to that differing rain intensity. So that analysis led to determining the flow rate and the sediment introduction rate using these specific regional factors. So we further conducted research through a GIS analysis, and we used a raster clip to identify specific regions. So the regions that we looked at are Luss Hills and Luss and Glacial Drift, and that is on the southeastern and the southeastern side of the state, and then the northeastern side of the state. So really that whole eastern border is kind of what we covered because they experienced higher rainfall, and we decided that that would be where we focused in for the state. So we averaged their K factors, which is erodibility, their P factor, which is the 2-year 24-hour rainfall depth, and then their curve number, so the average CN. So you can see that we did an analysis of just the Luss Hills, which is that highest experience one, and then we averaged the 2 regions, which is in that right column of the table. And that kind of helped us determine what our testing capacity could be. So this is how we determine the flow rate through hydroflow hydrographs on Civil 3D. And we were able to find the peak 30 minutes. So the 30 minutes that experienced the peak rainfall of that 2-year 24-hour storm, we averaged that flow rate. And then we also found peak flow rates, and these were for a 0.5 acre and 1 acre different dimensions. And I think it's important to state here that for the silt trap, we used a 1/2 acre drainage area in testing. And then for the sediment trap, we used a 1 acre drainage area in testing. And that was just due to the testing constraints at our research facility. So what we would actually be able to provide as far as soil and water for testing. And then we move into the sediment introduction determination, and we use the muscle equation. So the modified universal soil loss equation gave us our sediment yield, and you see the equation at the bottom and the corresponding factors. So that event peak discharge, we use the average peak 30 minutes because that would be more likely sustained than just the actual peak flow. And then most of the factors for both the silt trap and the sediment trap are the same moving forward until you get to the practice factor. And this is where we determine the silt trap, being a smaller contributory drainage area, would have less practices upstream than a sediment trap would, which would serve a bigger area and hopefully have more practices put in place. And that's the difference between those two practice factors. So to finish up our stage 1, we identified the silt trap and the sediment trap as that 1/2 acre and 1 acre testing range. And then that gave us our actual testing data. So we have a 0.5 CFS flow rate for the silt trap, 1.0 average flow rate for the sediment trap, and then the corresponding sediment loading would be broken up into basically pounds per minute that we would add into testing. And that's, you can see the sediment load, the difference there. So next we had to actually figure out what this roadside channel and testing apparatus was going to look like. So I included a cut section and channel profile. So it was a standardized highway construction roadside channel, and we pulled these from the manual charts, so that NDOT manual. The first 55 feet of our channel was at a 5% slope because that's kind of the middle range of steepness, and the theoretical impoundment would remain within the testing location constraints because we only had so much land to work with. And then the silt trap would be situated near the end of that 55 feet. And then in that 20 feet, which is at a 3% slope, would be the mouth of the sediment trap. So kind of level out a little bit before it makes that 90-degree turn. And then, like I had kind of mentioned earlier, it was the 10-foot width with the 30-inch depth. So our testing apparatus for water quality collection sampling, we decided to use just little plastic containers to collect the samples at the different locations we would determine. For the sediment introduction, I mentioned that buckets per minute or pounds per minute. And so we used 60 buckets and added dirt every 30 seconds over the entire 30 seconds. So lots of dirt. And then each was weighed out according to the corresponding silt trap or sediment trap weight. And then our testing apparatus in the right picture, you can see the blue kind of trough that has a calibrated weir. So we were able to regulate our flow rates through that trough. And then the red trough in front of the blue is the mixing trough. So water would pour out of that weir and we would dump the dirt at the top, and that little arrow in the middle would help mix it up before it flowed downstream to help simulate what runoff would actually be on a project. So stage 3 was determining that data collection. So we had 3 collection points: an upstream, in the trap, and then directly downstream. And then for the silt trap and sediment trap, you can kind of see they're very similar with those 3 locations. So the upstream helps us get that inflow, so what runoff actually is coming in, and then the downstream is really the other part that we looked at to make sure that it was leaving cleaner than it came in. So stage 4 was that sediment retention. So we had to determine how we were going to make sure that we were able to compare our sediment capture from installation to installation. So first we would do clean out. After all the tests per installation were run, we would have one clean out, and that's where you can kind of see in the left picture, we would have the skid steer and a hopper attached to the front of it, and we would drive down and shovel all the dirt into the hopper. And then in the middle picture, we have a huge industrial scale that we would set it on and then weigh that collected sediment from the test. And you can see there's a lot of water on top of that middle one. So we had to take moisture contents from each hopper, and that would kind of help us take out the water weight and really be left with the true sediment weight, so how much we actually captured. And this was the process we did for every single test. So the research methods, this is a kind of a cool aside. All the elements were accounted for in every method that we use, but our method for sediment retention did evolve over the period of this project. So in that far left picture, we have two very, very exhausted undergrads who had been shoveling all of the sediment into 5-gallon blue buckets, and then we weigh each bucket individually. And that was a lot of work. And then in that middle thing, we kind of have a very not OSHA approved setup with chains and the trough and lifting it up on this like scale with a hook that we would be able to see how much it was and then subtract out all the extra weight. And then finally, we were able to come up with another version, and that was the one I just described to you with the skid steer and the hopper and the industrial scale. So this kind of helped us become more efficient and also eliminate sources of error. And then in stage 5, we have our actual testing regime and each of the installations that would be tested. So for the silt trap, we have test A that would run 30 minutes. We would allow it to dewater, and then we would run test B, it would dewater, and then the final test C, and then that's when clean out would happen. So that was for each installation of the silt trap. And then for the sediment trap, it's very similar with that test A, B, and C. Instead, we would allow 24 hours to dewater since it's a much bigger practice. And then after test C, you can see there's only a 4.5 hour waiting time in between. And this was because we kind of wanted to simulate an overflow experience. So like a back-to-back storm. Test C and D would help us see how our practice would function, if it would actually be able to handle that much water that close in sequence. And then at the end of those 4 tests, we would do clean out for the sediment trap. So this was the identified plan for testing for each of the practices. We have the silt trap standard that would be tested first to see how just their standard would do. So we'd be able to actually compare whether these added installations or these added factors would help. We have an Excelsior wattle, a high porosity silt fence, a modified silt fence, low porosity, and then I'm not going to read them all out because they're already listed. And then we would identify the MFEI, we would test the MFEI, and then we went for the silt trap and did a few extra tests so we'd be able to compare it to the sediment trap. And that was kind of just to see if it's comparable at all and a little bit more on the research like what if side. And then for the sediment trap, there were really 2 main elements that we wanted to test, and because there were 4 tests instead of 3, we had to limit the number that we did just due to time and resources. So we identified baffles and the surface skimmer as those elements that we wanted to try. So the L in each of these testing numbers means longevity. So all these are longevity tests. We install it once, we test it the 3 or 4 times, and then we uninstall. And so that kind of helps you see better if it lasts over time. So the L means longevity. and then the I means installation. So now into the construction, which was my favorite part. We had to look at the stormwater research facility, and there are all these other practices going on, and identify where I could even fit this ginormous detention practice test setup. So here's kind of the area that we identified. So it's got a little bit of a weird shape, but that's just because of the 90-degree turn. You can see it from a different angle. We have the silt trap that would be tested in the left side, that skinnier side, through the channel. And then the sediment trap would be that turn at the bottom. And then the same roadside channel would be used, but we would just remove the silt trap when we transition to testing the sediment trap. So here's how it started. We were out there. I was learning how to fly a drone to kind of see what we were working with. So we staked it out, marked it out, and then started with the excavation. Like I said, construction was my favorite part, and that's purely because I got to work with heavy equipment, and not to brag, but I feel like I became a pretty good operator for the time that I had. But the flow is kind of coming at you, and you can see how we're cutting out this channel. And then we took back the side slopes to be able to get that from the plans that I had shown earlier. And then we continued and kind of finished that roadside channel on the left side of the screen and moved into that sediment trap basin, where we had to go pretty deep just because of the topography we were working with. So this is another angle of the basin itself. We dug it down according to the depth and that it needed to be. Then we would cut the side slopes as we're doing here. You can see that little ledge, and I mentioned the topography. The ledge dropped us down to get to what the actual height would be instead of us completely cutting back the entire way. So that's how we managed the work there. And this is kind of final product with the correct basin length and width according to the plans, the mouth of that sediment trap, and then the side slopes. So this was a look of the final graded roadside channel and the basin. The silt trap, excuse me, was not added in yet. But we were going to cover everything first because we wanted to minimize the erosion of the practice itself. So the channel would have added dirt had we run water over it. So to minimize that, because we couldn't account for how much would be included in it in our test, we decided to cover everything as a control. So let's get into the actual testing. We have the standard Nebraska silt trap, and that little picture in the bottom right corner shows you from what angle I'm taking these pictures, just to help orient yourself. So the flow is coming from that left side across to the right side of the screen, and I'm taking it from one of the corners. So we added in that silt trap. It was covered for that control reason that I was talking about. And then this is what it looked like during a test. So Nebraska doesn't actually require a practice in conjunction with the silt trap. It just has that excavated sump. And this is very similar to what we see in Alabama, and they pair excavated sumps with a rock check. So the next test was the Excelsior wattle, and this was one of the materials listed in the Nebraska manual. So there's different kinds and sizes, but this specific material and 12-inch diameter size was chosen to fit the high flow and low flow situations that were listed in that manual. So this is during a test, and in two separate studies by Donald and Schussler, they established that enhancing the installation procedure for the wattle would majorly help with performance overall. So you can see that the wattle is installed as a ditch check. It's spaced out stapling, so it has stapling alternating in the front and back to keep that wattle connected to the ground. And then we used a non-destructive TP stapling. So here you can see it never goes through the wattle itself. It only has kind of a slant to keep it connected to the ground and to keep it from kind of being washed down. and then the TP in the middle where we needed to overlap the two. So this was the wattle is further recommended to be put on an underlay without trenching, but we have that geotextile down as our control, so we didn't need to add that element. For the high porosity silt fence, this is a specific fence that Nebraska had used, and this is kind of called tennis court windscreen, and this is for high flow situations. As you can see, the material doesn't really create a lot of impoundment, which is what we had been looking for, and just allowed water to continue downstream. So it is not on the approved products list in Nebraska anymore, and the material has been completely phased out. So the low porosity silt fence is another fence that Nebraska uses, and it's of a woven material. And here you can see it's kind of in a U shape, and this is just because of our testing constraints. We had to turn the fence upstream to prevent bypass around it, and this just would typically go perpendicularly across your channel, but since we didn't have enough space to continue the side slopes up on this right side of the screen, you can't really see it, but our bank is a lot less steep. So we had to turn it upstream to prevent bypass. And then this is what happened during the test. You can see that 17 minutes into the very first test that we ran, we observed failure. And this is very in line with other research by Brian Roche that when he studied the low porosity silt fence, actually for Nebraska, there was this kind of failure when a lot of the water built up on the face of it and it couldn't handle the force. So our modified silt fence was a solution that we found by another study done by Dr. Donald at Auburn. And this found that there was a lot more manageable impoundment and 90% sediment capture in his test. And this is made of a non-woven geotextile. It's wire backed. It has an 18-inch cutout weir, and it's in a V shape in the channel. And here's a little bit more of the details. The wire backing gives it that support. And this actually gave us 35 feet of impoundment, which is the most seen in any of our silt trap tests. And this was kind of an ALDOT adopted fence, silt fence for the ditch check. So we kind of adopted what Alabama had done and used it in this Nebraska setting. So our temporary rock check, we had the Nebraska rock was specified to be a certain thing, and we found a conservative equivalent in Alabama to use as our rock. I'm not going to spend much time on this because it really didn't perform as well. You can see there's a little bit of buildup, but no real impoundment. So our modified rock check was a geotextile covered rock that had wheat poles across the face. Here you can see the rock was placed on top to hold that fabric down, so you weren't needing that stapling or any other type of secured method. And there was no trenching of the rock, and this was because many studies had shown that that was not helpful and really just adds expense. And then the geotextile generated higher impoundment, but the wheat poles were able to reduce excessive dewatering periods. So this resulted overall in increased sediment capture and decreased discharge turbidity than just a traditional rock check. So our slash mulch berm was the last thing we tested for this silt trap, and this was built in, no, it wasn't the last thing, my bad. It was built in 3 lifts, and it was firmly compacted in each, according to Nebraska. This is a great use of what is already on site if you're able to use wood that you've cleared out and chip it up, mulch it, and then use it on site. However, in Nebraska, you have a little bit less clearing that needs to be done, so the availability of fresh mulch would be a potential problem for sourcing this material. So the earth and burn was actually the last thing, and this was in the Nebraska manual as well. I hadn't found any literature on earthen berms, but it was also compacted in 3 lifts to really give it that stability. However, during testing, we saw that there would be a longevity problem. It was very apparent because after the 3rd test, it had eaten through half of the berm just from flowing over the back side of it. So here were our sediment capture results. So because the low porosity silt fence failed, it was not included in this analysis. And then we saw that the temporary rock check performed lower than the standard silt trap. This was not due to any, or the silt trap, standard silt trap being a higher performance than the temporary rock check, didn't have any sort of red flag there. It was just within reason. It's a 0.4 difference. So it's very small, but very comparable. And this was kind of as expected and shows that the rock actually doesn't add anything. But, oops, our highest performing one was the modified silt fence at 95.9% sediment capture, closely followed by the slash mulch berm. We wanted to look at that correlation to impoundment. As we had stated earlier, we were looking for high impoundment because that gave higher sedimentation time and opportunity, and then slowed that velocity flow. So we noticed a trend that the higher sediment capture also had the higher impoundment links. So this was a really neat correlation. And the R squared kind of tells us how well of a fit it was. And it was a surprisingly apparent trend. So the settling patterns that we noticed were that downstream were a lot finer particles captured within the silt trap itself, and then upstream was that heavier particle. And then we moved into water quality results, and this is where we looked at TSS and turbidity. So you can see that the slash mulch berm and the modified rock check and the modified silt fence were very high performers here. And that's based off of the median line. So half the data points are above, half are below. And that range was compared to the inflow range, which is in gray on that far side. So we have another kind of water quality test, and this is turbidity, so the cloudiness of the water. And TSS, I should have said, was the total suspended solids, so the particles, the weight of the particles in water versus the cloudiness of it. So the turbidity focuses a lot more on the finer particles. And then we compared the standard, or what was already included in the Nebraska manual, versus the modifications. So the standards are in blue, and this is what Nebraska employs. And then the modified versions of these things, so the modified rock check with that geotextile cover, the slash mulch berm is a pretty new development that Nebraska has just recently adopted, and then the modified silt fence was adapted as well. And so you see that the modifications perform a lot better than the standards. And this is just neat to see that really when you do continue looking for improvement, it is out there. So our standards can continue to be improved, which is encouraging. So our summary of our testing results is that the modified silt fence had that highest sediment capture and highest impoundment length. And then our water quality results was that the slash mulch berm actually performed the best in both TSS and turbidity, and our modified silt fence was in the top 3 for both. And then that third practice was different on each one. So our MFEI we determined was this modified silt fence just because of that really high sediment capture and the high water quality results that we've seen. Here's a little bit more of the impoundment look at it. So it wasn't bypassed. The weir was engaged the whole time during the test, or almost the whole time. And this is the most impoundment that we had seen. And these are the details of the fence from each angle. So now we get into this structural clean water testing. And that is because of our low porosity silt fence failure. So because we observed this failure, this force that kind of pushed over the fence and the posts, we determined that there was a need to make this structurally stronger. And so we came up with a very similar testing regime to the silt trap, where we had the 3 tests, but each of the shades, as you can see, was a different flow rate. And this is because we wanted to make it structurally sound, so we needed to increase that flow rate. And then the 5 installations that we have identified change only 1, maybe 2 of the different factors of the fence. So our first installation was 24 inches high. The standard is usually 30. So it was folded down to get that 24-inch height and then zip tied through both of the layers, which kind of created a stronger attachment because the zip ties, the fence wouldn't be able to rip through as easily with a double layer than it would a single layer. And these are the stats that we found off of these. I won't go too much into it since we've already been talking a while. But the depth ratio and the impoundment ratio were based off of theoretical and then actual. So we put the actual over the theoretical. If it was a ratio of under 1, that means it did not perform as we thought it would, or not as much as we thought. If it was 1, then it met the theoretical expectations, and if it was over 1, then it exceeded the theoretical expectations. And then the max deflection was based off of the post. The T-posts, as you can see in this graph on the left, were charted from start position to end position, so after the 3 tests. And I would measure the deflection from the top of the post during each one, and to see how far at the end it moved from the start. And here we have a little bit of deflection on that center post, but not as much as we would see in some other tests that I'll show you. So installation 2 was that 30-inch standard height, but instead of 5-foot spacing, we moved it to 2.5-foot spacing. And then we saw we had a pretty high max deflection, but our impoundment ratio on the last flow rate was pretty high, very close to theoretical. So installation 2, that orange line kind of showed the arc that you can see in the picture, but installation 2 also experienced the ripping around the zip ties that installation 1 did not have. Installation 3, we adapted the same V-shaped silt fence. We did 3.5-foot spacing just so it would hit the toe of the bank and then the center of the channel. And so that's the 90-degree spacing that would worked out in this 10-foot channel. And then the weir height was 18 inches, and that was cut out and folded. So we see that we had the least amount of deflection that we've seen so far, and it exceeded many of the ratios. The actual exceeded the theoretical in quite a few categories. Installation 3 had very minimal deflection, as you can see on the graph, and then this is the picture after the 3rd test. So installation 4, we tested wood posts, and as you can see in that bottom picture, it did not go as expected. The only thing that changed was the wood itself. The height and the spacing remained the same. And just because I love failure videos so much, I had to include it. And this was a drone shot of that test. You can see a lot of water gets through. And here's another angle. So that wood post, the pressure that built up on the fence, it just snapped the center one and came rushing downstream. Last video, I promise. But I just think it's so neat to see it fail, which also means that I could stop testing at that time, so it was great. Installation 5 was a 24-inch height and 2.5-foot post spacing, so we changed both of those, and that was a combination of installation 1 and installation 2 for a possible MFEI. There was still quite a bit of deflection, however, structurally it performed a lot better with the zip ties not ripping through the fence, and then the impoundment ratios were pretty high as well. That end post, I believe, was already slanted to begin with, so there was problems with the soil and getting it in because it had been so dry recently. But we see that there was still less deflection than installation 2. It was higher than installation 1, but that could be due to the tilt that was already there. And then our structural clean water MFEIs were installation 3, which was a very clear winner, and then installation 5, which could be very comparable. Sediment trap testing. we have the standard, and then this is the same diagram to help you know where I'm taking the picture. So I'm taking it from that rock weir. The standard has nothing in it, and we ran tests. This was during the test. You can kind of see a unique aspect to this was that in the basin, it would overflow back into the channel and kind of created more storage volume and lended to the impoundment benefits that you saw during silt trap testing, because the water would slow down way up here and then make it in. But this was during or near the end of a test, so it took a while to build up this volume if it wasn't already there. This is a picture of it hitting that 90-degree turn and coming in to that sediment trap. However, this was 24 hours post-test. You can see that it holds water for very extended periods of time. This was 24 hours, like I said. It wasn't in the channel anymore. You can see in that right corner, top right corner, it had already filled or trickled into the basin and out the weir, but it was still holding plenty of water and was not going to disappear anytime soon. So our next step was to see if we could create a little bit more of that slowing down early on rather than waiting for it to backflow into the channel. And you can see in this video that we really did achieve that, especially on the first baffle. You saw the most benefit when the water hit it. That turbulent flow is on the left side of the fence, and then you see a lot more laminar conditions moving further into the basin or the trap itself. And this was an after the fact picture, and you can kind of see how a lot of the heavy particles settled before that first fence, and then it looks a lot finer in the other remaining bays. So the skimmer was the third installation that we tested, and this allowed dewatering throughout. This was two different angles. We sized it for the basin itself, and after 24 hours, this was probably more around like 30 hours when I took this picture, but you see that the skimmer had already returned or restored that storage volume, so if any other storm came by, that it would be able to hold the volume for that storm rather than just letting it continue on since it was still holding like the standard did. But it watered a little bit too fast, and that was because the inputs that I used were based off of the volume rather than the actual dimension. So I forgot to factor in that weir kind of height. And then our MFEI we determined was going to be the baffles because of that slowing down feature that we had noticed in the video. And then the skimmer because it would restore volume. And the spacing's a little bit funky because I was following where the other baffles were. However, because I added a skimmer, I had to scrunch that last one because the skimmer needed to be in the deepest part. But you can see that our baffles were not overtopped or bypassed, and that the skimmer's hiding, but it's going to start restoring that storage volume. And this was the same kind of slowing down effect that we saw. And then after we did our sediment capture analysis, the baffle installation did the best, closely followed by the MFEI. It was within 0.8%. And all of the installations were actually very close, but from the standard, our MFEI increased the sediment capture by 4.7%. And then in the water quality results, I'm just going to kind of go through this pretty quickly because they are very similar in as far as they actually improved from the inflow. But you can see in the turbidity, we have a problem with the MFEI. So we looked further into that and we split the inflow to see if there was a difference in inflow from the 2 tests or from the 3 tests versus the 1 test. There was no difference, and that was because the flow was already at sediment loading capacity. And so we looked at the background turbidity. So this is the pond water that we used. And we see that the pond water for the MFEI was a lot higher, like as far as turbidity goes. That's because it had been super dry, very low ponds, and then we got a rain, so everything got suspended again and stirred up, and I had to get a test done. So unfortunately, we weren't able to retest, but we found the reason why it was so much higher. And then we looked at TSS, and you see that it's really not higher. than the others, not significantly. And so this is because the TSS is more on the weight of the particles and turbidity is more on the cloudiness that I had mentioned earlier. So the finer particles are the ones that are suspended and gonna affect your results. But we still determined that our MFEI was the baffles and the skimmer because of the other benefits that we saw as far as the settling of the heavy particles and then the dewatering or the restoring volume. So our conclusions, since I talked so long, I'll just let you kind of look over the key findings. Really, in both situations, we were able to enhance the practices as far as sediment capture and water quality, as well as some other added benefits. There are a few things that we would love to do for future research, if possible. Either adding different elements, and then for the skimmer, I would most definitely try to aim for more of a 48-hour dewatering. And that would just be based off of the volume or the actual dimensions rather than just a known volume. And then the benefits for Nebraska were really overall to improve their water quality. But I'm going to go ahead and wrap up and see if there is any questions.
Hello. Okay. Wow, Lee, that was really, really great. Thank you for sharing this research with us. We do have three questions in the Q&A panel. So I'll quickly ask that and then hand over to you. We have a question from Andrew Patterson, and he asks, how did you ensure you were only collecting in sediment introduced into the experiment? It looks like there is a black tarp, but I'm not certain. And I think you did touch a little bit on that when you were talking about the construction of the research. But I think I also want to add, even with the black tarp, was there any other possibility of having other sediment that was collected while you guys were running the tests?
There is always a possibility just because we are very dependent on kind of what's going on in the climate. We did as much as we could as far as like being very specific and weighing out the sediment and that tarp, or it wasn't a tarp, but it was 8-ounce geotextile that we covered everything in as that control. But as much as we could, we made sure that no extra sediment was coming in.
Right. Okay. Thank you. We have a question here from Destiny Williams. She said, is there a way to make the wood post work with a different shape, or would you just recommend using steel posts? I believe that was
I
for
think
the steel trap.
So that honestly would be really cool to look into. I feel like if you maybe reduce the post spacing or even did that V shape and reduce post spacing, that you would get a little bit better performance, but it's still a lot of pressure on the wood and it's snapped at the base. So that would be cool to look into.
Yeah. Great. We have an attendee here who also asked, how did you repair the holes made by the post to prevent saturating the soil and affecting subsequent tests?
So we would replace the geotextile. If like when we used a lot of the posts for the fences, we would have to completely take out that strip of the geotextile and repair it, like replace it. So that's how we would minimize the holes affecting the tests.
All right. We have two questions from Mark Gonzalez. First question being, have you tested any of the newer two-stage silt fence materials now available? And then his follow-up question is, are sediment traps still recognized by ADEM?
So for the first question, I don't believe I have been able to test the newer silt fence materials. I know that in the research group that I was a part of at Auburn, that they are continuing to look into that and have a lot of upcoming projects. So maybe they will get to. I would love to hear about it though. And then for that second question, sediment traps are really, the names vary across a lot of DOTs. And so you see sediment traps, sediment basins, silt trap, all of these are really essentially performing the same way, like the detention practices function off of the same principles. However, they're just called something different. I hadn't seen anything that said that it wasn't recognized by ADEM, but I also
Mm,
didn't concentrate in Alabama
okay,
um, as much as Nebraska.
right. Okay. Thank you so much for that. I believe that is all the questions that we have. Since there's no other questions, I think we'll just wrap up the webinar here. Again, Lily, thank you so much for taking the time to present today. Thank you to everyone who was able to join. We hope to see you in the next TigerStream webinar.